Welcome to the first lecture of module 3 on heat transfer.
In this lecture, we will discuss on one-dimensional unsteady state conduction heat transfer. Till last lecture, we have discussed on steady state conduction heat transfer, but here we are concentrating on unsteady state situation. And as we understand from unsteady state point of view, unsteady state conduction heat transfer means that heat conduction takes place under transient condition, where the temperature at any location is function of time. At the same time, it can be function of location also at any time, it can be function of location or position also. Now, depending on the situation, it can be one dimensional, two dimensional or three dimensional heat conduction. We will be mostly concentrating in this lecture on the one dimensional heat conduction. That means, temperature is a function of one direction of, or rather one coordinate in the direction of heat transfer, and also temperature will be function of the time of heat transfer. So, and this unsteady state heat conduction phenomena is a very very common process, common situation in industrial processes, is very frequently encountered. Typical industrial processes, if we see that it includes like heat treatment of metal parts, annealing operation, then hot rolling of metal or an alloy to a sheet, then heating a furnace to a steady wall temperature, then heat gain or loss by the buildings, certain changes of environmental temperature, when the suppose there is a pipeline, there is a transport is taking place of say oil transport, or it could be water transport, then which is that pipelines are buried under the earth after certain depth, and there can be atmospheric temperature is suddenly reduced, particularly in the winter seasons. So, there is also a situation when the temperature is suddenly changed. That kind of situation is a practical examples of unsteady situation, which may not be related to directly to the industry, but which may be related to the common life of the human beings. Similarly, cooling of IC engines, then startup and shutdown processes in many of the industrial processes which involves heat generation or which involves heat transfer in it, then all the startup and shutdown processes, they do encounter an unsteady state situation, as well as there are certain energy recovery from hot gases by thermal regenerators are used for energy recovery, particularly example is that hot energy recovery from flue gas. So, hot gases, energy recovery from the hot gases in the thermal regenerators. So, these are typical examples of several industrial processes where unsteady state heat transfer takes place. Okay. Now, when we say about that, then there are various models which are used for unsteady state conduction analysis, and this unsteady state conduction analysis is very much needed, because we have to know that how is the temperature profile within a material, how the temperature is varying from one place to the other place of the material, and once we know the temperature, then only we can calculate, if we want, how much is the heat requirement for further heat requirement, or how much will be the heat transferred from the material to the environment. So, this information, time to time information on all these things are very much necessary, and therefore, the analysis of unsteady state heat conduction is necessary. And for that, there are two type of models, as I told are there. One is called lumped parameter model, another is called distributed parameter model. Now, the question is, what is this lumped parameter model? In the lumped parameter model, as you understand from the name itself, the parameter is lumped over the entire body, and in this case the parameter is nothing but the temperature. We are interested about the temperature. So, this temperature is lumped over the entire body of concern. Okay? And therefore, what does it mean? That means the temperature is uniform, assumed to be uniform. It may not be exactly uniform, but it is assumed to be uniform throughout this body. Therefore, there is no variation of temperature within that body of concern or body of study, but temperature is a function of time at any location of that body. Okay? So, this kind of situation, that LAMMPT parameter model kind of situation appears when there will be almost no resistance in the body. That means what? That means the thermal conductivity of the body is very high. That means within the body, the heat is being conducted very fast. So, there is no resistance, almost there is no resistance, and therefore, it is assumed that the temperature variations from one place to the other place of the body is almost negligible. Okay? So, this LAMMPT parameter model is applicable for cases when a material is having very high thermal conductivity and the material is of smaller size in general. Okay? We will discuss these issues a little later. Then another model is distributed parameter model. Now, from the name itself we can understand that in this case the parameter is distributed over the material. That means, the temperature is the parameter here in the present case, and the value of the temperature is distributed over the entire body. That means, from one place to the another place of the body, temperature is varying. Okay? At any time from one place to the another place of a body, the temperature is varying, and therefore, it is called distributed. At the same time, at one particular location of the body, the temperature is function of time. So, thus in case of distributed parameter model, temperature is a function of both time as well as location in the entire body. Okay? There are two type of problems we will be discussing, because distributed parameter model is a huge area. We don't have enough time to discuss on all these, because there are many other aspects of heat transfer has to be covered. So, distributed parameter model or heat transfer, unsteady heat transfer, when the distribution of temperature is there, when temperature is a function of time and coordinate, there can be lot of analysis can be done in this area. But what we will do is, for some understanding, for certain understanding of undergraduate chemical engineers. So, what we will try to do, we will concentrate on one dimensional heat transfer first of all, and second thing, there are few cases we will consider, and we will see that how the temperature profile is existing in a body, and as well as how to find out the heat flow rate, and how to find out at different location at different time the temperature as well as heat flow rate for this are subject to certain conditions, subject to certain coordinates. We know that there are three coordinates existing: Cartesian coordinate, cylindrical coordinate and spherical coordinate. So, we will see that in case of say Cartesian coordinate, that means in case of plane wall, for example, that building walls, which is a plane wall, example of a plane wall. So, what happens for that case, unsteady heat transfer, how is the temperature profile, how is the distributed parameter system model is applied in this case. Similarly, the case of a cylindrical body, for example, we know that dryers, then distillation columns, these are of cylindrical body, and there is a high possibility that distributed parameter model is applicable for those kind of situations. Similarly, for spherical vessels, large spherical vessels, also we can have such kind of situations. So, we will discuss in all the three different geometries that how distributed parameter model applies. Okay? And also there are two situations we will discuss, as I have shown. One is the case for transient heat flow in a semi infinite solid and an infinite body subject to sudden convective environment for heating or cooling. We will discuss this issue subsequently in different lectures. Okay? Now, thus there are two problems, as I told. One is the transient heat flow in semi infinite solid and infinite body subjected to sudden convective environment for heating or cooling. These are the two different cases, problems for one dimensional problems of unsteady heat transfer, and this is a distributed parameter model cases. And now, solution for this kind of situation is not very easy, these are little complicated. So, therefore, we will be concentrating on one dimensional, because three dimensional cases are more complicated. So, we will be trying to simplify the cases as much as possible and see just to have an understanding that how temperature profile is there. Okay. And what we will do is that there are a few ways of doing the solution of this particular cases, and what we will do, there are two different ways of solving these. One is the analytical solution methods, another is the graphical solution. Practically analytical solution method means here the things will be solved by separation of variables method and combination of variables method. So, we will discuss we will take up one cases for separation of variables and combination of variables, how the heat transfer problems can be solved. And then graphical solution, actually in this case also the temperature profile is being developed by somebody else. He has already worked out and has been given that temperature profile has been given in the form of figures, in the form of graphs, and now for our training purpose, for our learning purpose, that students, in fact for practical applications also, so we can find out how will be the temperature for a particular situation and how to find out this temperature from the figures or the chart available. At the same time, not only the temperatures at different locations of the body, but the heat flow rate also can be calculated, can be found out with the help of the various charts or figures available. So, we will see that with the help of certain problems how to make use of these charts. Okay. So, now to start with, what we will do is we will start the case of unsteady state heat transfer phenomena, and we will start with lumped parameter model. Okay. Now, lumped parameter model, as I discussed with you, that it is dependent on the situation when the temperature is lumped or parameter is lumped in the entire body. So, what we will do is, let us consider typically a body. Let us consider typically a body. Okay. This body has a volume is equal to V, equal to volume, and let us write like this way, otherwise we will confuse with velocity. So, let us write this is the volume and this is the area of heat transfer. Okay. So, this is some object which is, say the object is hot and it is in some outer environment. Okay. This is the environment where heat is being transferred from this. So, say if I say that heat is being Q dot, the heat is being transferred to the environment, and let us say that environment and temperature is T infinity is the temperature of environment, and T I is the temperature of the body at T equals to 0, that means the initial temperature of the body. Okay. Now, what will happen that T infinity is less than T I, that means the heat will be transferred from the body to the environment. Now, what we will assume that as that is the lumped parameter model case, as because it is a lumped parameter model. So, temperature is uniform through this. Now, what is happening with time? What is going to happen that energy, that internal energy of the body is going to come down. So, the body is going to lose energy, heat energy or its internal energy, and it is getting transferred to the environment. So, the energy that is being lost by the body will be reflected with the help of or in terms of decrease in temperature with time. So, what we will write is that if rho is the density of the body and V is the volume as I discussed. So, this is the mass and Cp is the specific heat, okay, that means which is the heat requirement per unit kg per unit mass. So, rho V Cp m Cp into dt by dt, that will be the change in internal energy, and because it is going to a lower temperature. So, dt by dt is a negative quantity. So, change in internal energy we will write it as minus of this. So, this becoming the total thing is becoming positive. Change in internal energy would be equal to the amount of heat lost which is to the environment, and that is being happening with the help of convection. So, it is an example of conduction and convection phenomena that is taking place in tandem, it is taking place together. Okay. So, heat is being conducted from the body to the surface, and from here it is the convection phenomena that is being happening. Okay. Then we will write it that H is the heat transfer, convective heat transfer coefficient, okay, and A is the area of the body, that is the area, surface area of the body, and we understand that in case of sphere it is 4 pi r square, in the case of cylinder it is 2 pi r L into 2 pi r L plus 2 into pi r square, that is 2 end of the two areas. Similarly, in case of Q it will be 6 into side square like this. So, this will be the surface area of heat transfer. Okay. Surface area of heat transfer means that the area which is exposed to the environment for the transfer of the heat. Now, so H A into at any time t is the temperature of the body minus, this is the as per the Newton's law of cooling, that heat transfer is H A delta T. So, we are writing that T minus infinity is the same equation. Okay. Now, this is a very basic equation for the equation of energy balance that is being happening. The rate of change of internal energy is nothing but equal to the rate of heat transfer by convection from the solid body to the environment. Okay. Now, from this if you just simply do little calculations, then what we will get at T dt by say T minus T infinity, and if we integrate from T is equal to T I to T is equal to T, okay, will be equal to minus H A by rho into C P into V, okay, into d T, okay, and this is equal to at T equal to 0 or at T is equal to initial temperature and T equal to T. And what we will assume that other areas, naturally volume and area are not functions of time. Also we will assume that H, rho and C P are independent of time. Okay. They are constant quantities, and thus what we will get is, if we do the integration, we will get that T minus T infinity by T I minus T infinity equals to e to the power minus H A by rho C P into V into T. So, this is a very common form of equation. Now, we can say that at T equals to say tau, and tau is equal to rho C P V by H A. Okay. At T is equal to tau and tau is equal to, so if we say that, then what we get, that T minus T infinity by T I minus T infinity, we will say that it is minus e to the minus T by tau, tau is equal to rho C P V by H A, and when T is equal to tau, then for this case we will get T minus T infinity by T I minus T infinity, and that is equal to e to the power minus 1, e to the power minus 1, and this value is equal to 0.368. Okay. So, what does it mean? It means that T minus T infinity equals to 0.368 of T naught minus T infinity. Initially, this was the temperature difference between the body and environment, and after time constant t equal to tau, after the value of tau, that value is reduced to 36.8%. So, at sorry, t equal to tau, t minus t infinity by t naught minus t infinity is equal to 0.68368. That means, at time t equal to tau, that temperature difference in the body is becoming 36.8% of the original temperature difference. Okay? That is the definition of a time constant. So, tau is called, when tau is equal to rho Cp_v by Ha is called time constant. So, time constant is the time. So, the unit of rho Cp_v by Ha is time. Its unit is. So, time constant is a time that is needed for the temperature in the body, temperature difference in the body to reach to 36.8% of the initial temperature difference. So, initial temperature difference was T naught minus T infinity, and after time constant the temperature is T minus T infinity, and this T minus T infinity is becoming 36.8% of T naught minus T infinity. So, this is called the time constant, okay? And rho Cp by Ha is called the time constant. So, this is one very important information that we can develop from this, and in future when we will be studying any first order processes, we will be learning about this time constant. So, this is also viewed to be a first order process. Okay? Now, drop in temperature in the body is viewed as a first order process. Okay. Now, if we go for further analysis of this, say for example, we have got the expression that Ha by, if we do little bit with this, rho Cp into V, that is the inverse of the time constant. If we write this in a little organized way, what we will do is we will get H into V by A by K into K by rho Cp into V by A whole square. This is the expression that we are going to get. Okay? And we say that V by A is equal to say L, this is a characteristic length, and that we can very easily understand that V by L is the characteristic length, because V is the volume, unit is volume, and A is the unit is the area, is meter square, and V is the meter cube. So, V by A is the unit of length, and we will say that V by A is the characteristic length. So, we will write this is as H L by K into K by rho Cp. We know that K is the thermal conductivity of the body, and rho Cp we know that alpha K by rho Cp is the thermal diffusivity, which is meter square per second, and V by A you will write at L square. So, then in that case we can write that T minus T infinity by T I minus T infinity also can be written as e to the power minus Biot minus H L by K into alpha by alpha T by L square. So, this is also written as e to the power minus B I into F O. This B I is called Biot number. So, this is your H L by K. This can be written as 1 by K A divided by L by K A divided by 1 by H A. We know that L by K A is the conductive resistance. We have seen already in case of conduction, and 1 by H A is called the convective resistance. So, this is Biot number is becoming a ratio of conductive resistance to convective resistance. Okay? This is conductive resistance to convective resistance. And both are for heat transfer, convective resistance for heat transfer and convective resistance for heat transfer. So, it is a ratio of two resistances, one is convective, Biot number is a ratio of conductive resistance to convective resistance, okay, for heat transfer. And the important point over here is that if Biot number is very less, then we can understand the conductive resistance is very small. Okay. Another point we should say here, that the conductive resistance what we are discussing here, this is called a solid conduction. This is a solid heat transfer, conduction, heat transfer or heat conduction by the solid material. Okay. In future, in subsequent lectures, we will be coming across another terminology, that is called Nusselt number, which is denoted as Nu. This is also having a similar physical significance, that it is also can be expressed as conductive resistance to convective resistance, but the difference between Nusselt number and the Biot number is that in case of Nusselt number we are telling about the conductive resistance of the fluid. So, this Nusselt number terminology exists when there is a heat transfer between a solid and fluid. So, Nusselt number says the conductive resistance of the fluid, whereas Biot number says the conductive resistance of the solid. So, this is the major difference lies between Nusselt number and the Biot number. Okay. The other terminology, that is called Fourier number, FO, and this is, we have seen that it is expressed as alpha t by L square. Okay. Now, this can be, this is usually expressed as, this is, or this is written as, if we say that it is an indication of that degree of penetration of heating or cooling effect. Degree of penetration of heating or cooling effect through the solid. It is also can be expressed as the temperature penetration depth by body dimension. So, alpha into T is the temperature penetration depth, and it is related to thermal conductivity. So, how much thermal profile, temperature profile has penetrated into the body with time t, and L square is the body dimension. So, this way a Fourier number is also a dimensionless quantity, and that is defined. Thus, we can say that T minus T infinity by T I minus T infinity is equal to e to the power minus Biot into Fourier. Okay. And also we have seen that Biot number is the ratio of thermal conductive resistance, conductive resistance to heat transfer to convective resistance to heat transfer, and also I told that when the Biot is very small, that means conductive resistance is very small. Okay. So, what we told at the beginning that lump parameter model is applicable when the temperature variation in the body is negligible. That means, the thermal conductivity is very high That means thermal conductive resistance within the body is very low, that means the Bayer number is very low. So, it is expected that lump parameter model will be very much applicable when Biot number is very low. Okay. For Biot number is very low, that lump parameter model is very it can be applied, and it is being reported that if Biot number is less than 0.1, then lump parameter model can give a reasonable estimate, and that is within 5% of the error. So, if Biot number is less than 0.1, then lump parameter model can give an estimate within 5% of error. So, what is being suggested is that, or recommended is that, because there are always a good amount of uncertainty involved to calculate in the calculation of value of H, convective heat transfer coefficient, that uncertainties sometimes rise within 25% of this 25%. So, this is a huge uncertainty is there in calculating convective heat transfer coefficient, whereas the uncertainty while getting using lump parameter model, if the Biot number value is much less, is within 5%. So, therefore, it is advisable that one, when trying to find out that heat transfer rate or flow of heat or the temperature profile in a body, first try out whether the lump parameter model is applicable or not. That will actually make the cases simpler. Okay. Now, what we will do that there is some thermal network for single capacity system. Here we will say that it is a for a single body, it is a single capacity system. So, there we can draw a thermal network for that, just in analogous to electrical system. If we see that T I is the some temperature, and okay, and so this is say T infinity environmental temperature, and there is say switch is there here, and this is sorry. This is 1 by H A, this is equal to R resistance, and this is the capacitance, this is equal to rho C P into V. So, this is a thermal network for single capacity system. If we try to understand here, the situation is like this. This is a switch, and what is happening that there are two potentials T infinity and T I. T I is the, as I told, that T I is the initial temperature of the, that means of the hot body, and T I is the environmental temperature. So, when you put the switch on, the body is charged, the capacitor is charged with this potential. Okay. So, this is the potential difference for the capacitor. The capacitor is charged with the thermal potential of T I, and then once we switch off, then what will happen? This energy will be released through this resistance, through in this circuit, this energy will be released. So, the capacitor is holding that energy, it is getting charged, holding the energy, which is equivalent to the potential difference of T I minus T infinity, okay, at the initial condition when the switch is on. And once you switch off, when the switch is made open, okay, then what will happen? That this circuit is disconnected. So, this energy will be released through this circuit. That means that energy will be released to the environment, and where the resistance is 1 by H A. Okay. So, this is way that in this case also, in our present case also, that 1 by H is the environmental resistance. So, from the surface, if you see here that from the surface of this, it is getting to the environment with the resistance of 1 by H A. Okay. So, this is some understanding about that representation of the Laurent parameter model system in the form of thermal network for single capacity system. Here it is a single capacity because we have only one body and that is energy stored in that particular capacitor. Okay. Now, what we will do, we will take up problems on these particular issues. We will discuss a few problems. So, let us discuss a problem, say question 1. An aluminum cube of side 5 centimeter and at 100 degree centigrade temperature is suddenly exposed to air at 25 degree centigrade. The convective heat transfer coefficient is 25 watt per meter per Kelvin, watt per meter square per Kelvin. Rho aluminum is equal to 2700 AL 2700 kg per meter cube and K aluminum is equal to thermal conductivity 215 watt per meter per Kelvin. Okay. And Cp specific heat of aluminum is equal to 0.9 into 10 to the power 3 joule per kg per Kelvin. Okay. The problem is calculate the time required for the center temperature to reach 40 degree centigrade. Okay. So, this is the problem. The problem is that there is an aluminum cube, okay, of side 5 centimeter, and it is at 100 degree centigrade temperature, and it is suddenly exposed to air, okay, which is at 25 degree centigrade, and it will be losing energy from the cube to the environment. So, if it loses the energy, then we have to find out that it will be at some time it will be reaching a temperature of 40 degree centigrade. So, what is that time? That is the question. Now, before we proceed for Laurent parameter analysis, we have to first check whether the Laurent parameter analysis is applicable or not. So, the checkpoint is that we will check the Biot number. If the Biot number is less than 0.1, we will say that Laurent parameter model is applicable. So, we will calculate Biot number. Biot already we know that is it is H L by K, or it is H into V by area by K. Now, here we have to see that it is a cube, Okay. So, for cube, volume is equal to, we know the length square, length cube, and what is the area, surface area. All the surfaces of the cube is exposed to the environment. That means there are 6 surfaces which are exposed to the environment. So, what we will get is that V is equal to 0.05 whole cube, and this is meter cube. Okay. 5 centimeter, 0.05 meter. So, 0.05 meter cube, that is volume, and area is equal to 6 into side square. So, 0.05 whole square, this many meter square. Okay. So, we will get V by A is equal to, if we do the calculations, we will get that is equal to 5 by 6 into 10 to the power minus 2 meter. And then what is the value of Biot number? If we do the calculations, we will see that it is equal to 8 equal to 25 into 5 by 6 into 10 to the power minus 2 divided by K is for aluminum 215, and the unit of Biot number is, it is a number. So, it is unitless, and this value is equal to, if we do the calculation, 0.00097, which is much less than 0.1. So, that with this, so this is the check. With this check, we can say that Biot number is much less than 0.1. So, lumped parameter model is applicable. That means, what we are writing conclusion from this check is that lumped parameter model is applicable. So, once lumped parameter model is applicable, now we will enter into the equation temperature for finding out the temperature profile. Actually, we know the temperature, we have to find out the time requirement for certain change in the temperature. So, we need to have the temperature profile. So, temperature profile we have already seen that T minus T infinity T minus T infinity by T I minus T infinity and that is equal to e to the power minus Biot into Fourier. Okay. And Biot number values we have already seen. Now, for Fourier number, what we have? Fourier number we have, it is alpha t by V by A whole square, right? Alpha t by L square, L means V by A. Now, actually what you have to calculate in this problem, we have to calculate this temperature, we have to calculate this, we have to calculate this time. So, what we will do is, we know that ln T minus T infinity by T I minus T infinity is equal to minus ln this is equal to Biot into Fourier. Okay. So, this value is known to us. So, for my case, if time for the time which is wanted, at that time T is equal to 40 degree centigrade. So, we will get minus ln, this is 40 minus the T infinity is 25. So, here whether it is we are writing in Kelvin or in centigrade scale does not matter, because it is finally we are getting the difference of the temperatures. So, 40 minus 25 by we will have 100 minus 25 and that is equal to Biot into Fourier. So, or minus ln 15 by 75 is equal to Biot into Fourier. So, we can say the Fourier number is equal to minus ln this is equal to 1.61 by Biot number, and this is equal to 1.61 by 0.00097. Okay. And then what we say is that alpha t by V by A whole square, and that is equal to 1.61 by 0.00097. From there we can say that alpha t equals to, that is the time requirement, that is what we have to calculate. It is 1.61 by 0.00097 into V by A whole square is 25 by 36 into 10 to the power minus 4 into alpha, it will be 1 by alpha. 1 by alpha is equal to that we have to calculate alpha. Alpha is equal to, we have seen that it is 8.85 into 10 to the power minus 5. How to calculate alpha? So, we will be calculating alpha like this. Alpha is equal to k by rho C p, and the values are given to us. K is equal to 215 by rho is equal to 2700 into C p is equal to 900. So, this gives that 8.85 into 10 to the power minus 5 meter square per second. So, if we put these values here, and then we will get that this value becomes 1302.4 second, and that is equal to 21.71 minutes. So, that means that the cube, the aluminum cube will come down to that temperature 40 degree centigrade temperature at 21.71 minute. So, this is the problem. Now, let us see another problem. So, question 2, it says that a copper ball of 5 centimeter diameter of initial temperature 100 degree centigrade is suddenly exposed to ambient at 25 degree centigrade. Okay. The initial cooling rate is 4 degree centigrade per minute. Okay. Calculate the convective heat transfer coefficient. Assume that Laurent parameter model is applicable. And rho copper is equal to 8900 kg per meter cube, then Cp of copper is equal to say 380 joule per kg per Kelvin, and thermal conductivity K for copper is equal to 370 watt per meter per Kelvin. Okay. So, now the problem is there is a copper ball and the copper ball is losing energy. Now, as because the temperature of the ball is getting changed with time, we have seen in the previous that in the basic equation the temperature is changing with time. So, dT by dt, the rate of change of temperature will gradually decrease or will gradually change, because it is losing energy. So, at a very high temperature the rate of change in temperature will be much lower, much higher than that at the very low temperature, because the driving force will gradually decrease. As we know that in our previously what we have discussed, if you see that here that in this region there is a driving force is T minus T infinity, and this driving force will gradually decrease, as the time goes on, because the hot body will be gradually decreasing. So, then therefore, the dt by dt will go on decreasing. Okay. Therefore, dt by dt is will be changing, and so initial value is being given to us for this problem. So, what we will do is, and it will be a decreasing value, it is cooling, initial cooling rate is 4 degree centigrade per minute. So, we will convert it as, so dt by dt is equal to 4 degree centigrade. So, minus dt by dt, it is the cooling is 4 degree centigrade per minute, and that is equal to 4 degree centigrade by 60 per second. And now, if we see our basic equations, so rate of heat transfer is, we know from the basic equation, if we see that minus rho Cpv into dt by dt is equal to H into area into T minus T infinity, and dt by dt is given, rho is known to us, Cp is known to us, volume of the copper ball is known, and then surface area of the copper ball is 4 pi r square, that is also known. H is given, I have to find out, sorry, H is, T is known, so H has to be found out. So, that way we can find out that H is equal to rho into Cp into V into minus dt by dt by, we have area into T minus T infinity, and here the values are, rho is equal to 8900 kg per meter cube into Cp value is 380 joule. So, we have to be very careful about the units, and V is the volume, volume is 4/3 pi into r cube, it will be. So, actually let the problem will little be reduced, that it will let us make it to be a copper ball of radius 0.5 centimeter, we write radius 0.5 centimeter, if we write, then it will be that it calculations is accordingly. So, 8900 into 380 into 4/3 pi into 0.05 4/3 pi r cube, okay, that is the volume, into the cooling rate is 4 by 60 will come. So, we will write first, area is again 4 pi into r square is 0.05 whole square into 75 is the T minus T infinity is 75 into that, this 60 will come because of this conversion of degree centigrade per minute to degree centigrade per second. So, this value comes to be around 50 watt per meter square per Kelvin. Okay. So, this is H A delta. So, it is becoming 50 watt per meter square per person. So, this H, the convective heat transfer coefficient between the copper ball and the environment is 50 watt per meter square per Kelvin. So, we can calculate, even by doing some experiment, proper measuring of the temperatures, we can calculate how is the convective heat transfer coefficient using the Laund parameter model. So, what we will do is, we will stop here in this for this lecture. In the next lecture, we will discuss on unsteady state heat transfer for distributed parameter model system, when the temperature does not remain uniform in a body, where the temperature is varying with position in a body. So, we will discuss in the next lecture. Thank you very much.